So this is acids and bases. We're going to try to explain some of the more difficult topics. So now we're going to talk about the basic idea of what a buffer is, and we're going to use the example of weak acids as buffers. You could also have weak bases as buffers, but we're just going to go through weak acids, and then the same concept applies for weak bases. You just flip acid and base. So this K has to be less than 1, the weak acid that is, to make a buffer solution. So what a buffer really is that it means that once you've made the solution, if you add a small amount of a strong base or strong acid, the pH is not going to change much because essentially the weak acid sort of absorbs the blow of that strong base or acid, is maybe a way to think about it. And that's sort of why basically, if you look at the titration curve, there's a region where it flattens out, and in that region there's about as much HA as A minus. So basically, whether you add a strong acid or a strong base, the H plus or OH minus can be neutralized by either HA or A minus. Alright, so we're going to start out this titration with just a weak acid. The weak acid doesn't dissociate very much, but we're going to want to have a high concentration of it to make an effective buffer, so the pH is still pretty low. So there could be an example image of the titration curve, and the red dot shows that we're at the start of the curve right now. We're going to add a little bit of the strong base. It'll dissociate and then neutralize the H+, so the pH is going to go up, but it will not go up as much as it would have were there no weak acid present, because the weak acid is going to make more H plus to make up for that loss. Eventually the half equivalence point is reached after enough strong base has been added. At that point the solution's fully buffered, so it could buffer either a strong acid or a strong base, because the concentration of HA is equal to the concentration of A minus at that point. So pH is also equal to pKa, so there it's at the half equivalence point. We can continue to add strong base until the equivalence point's reached. At that point, all the HA is gone. It's all dissociated into A minus and H plus, and a lot of that H plus has been neutralized, which is why the pH at equivalence point is greater than 7. But that's also because mainly the Na plus, if we're assuming NaOH is a strong base, is not going to accept OH minus, but the A minus of the HA will accept H plus. So there we're at the equivalence point, and if you continue to add strong base after that, the pH is going to increase logarithmically, which is what you would expect if there were no weak acid there, because its pH is a log scale. So we're basically going to try to explain where the Henderson-Hasselbalch equation came from. So it's actually nothing more than the equilibrium expression, but just the terms are rearranged. So you'll see that. So basically just start with the equilibrium expression. Now let's say we're to take the negative log of both sides of that equation. Now you could think of the negative log, it's like the same as the negative of the group of all that. You'll see why I wrote it like this later. So I really haven't changed anything on the left or on the right. So now within that those parentheses, using the properties of logarithms, you can basically the log of a product of two things is equal to the log of those two things added. And now I'm going to redistribute the negative sign, so that's why I grouped it like that earlier. And then pH is just the negative log of something. So now we can bring back our P notation. And so what do you know? Look, that's the Henderson-Hasselbalch equation, and it's nothing more than the equilibrium expression. So if you're good at working with logs, you don't even have to memorize it. But otherwise, and even if you are, just to save time, it might be a good idea to memorize it. But that's where it came from. And that's the end.